much for having me. It's a pleasure to be here. Before we get started, can everyone hear me okay? Or it's not that good so that we are logistically fine? Can you hear me okay? Okay, perfect. All right. So at any point in time, if you feel that the sound is breaking or something like that, please put that in the chat. I should be able to see your chat as we proceed, but there will be someone from the team who will monitor. Okay. All right. So uh, we just have 1 hour or so, and I think this session would be recorded and is being recorded. And in case you miss out something, you can always rewatch and reach out to me later on over email or LinkedIn, whatever you are you are more comfortable with. And before we get started, I just thought to give you some pointers that what we are going to talk about so that you know what we are going to discuss in next 1 hour. So my objective here is to give you some brief about embeddings and how embeddings are useful in the context of large language model, but also in different techniques like RAG. If I get some time, I will cover that. Otherwise, maybe we can host some other webinar, or there are a lot of content on RAG on Data Science Dojo. You may like to refer to that. Okay, so I will share all the content, whatever I'm going to present. It's mostly a GitHub repo and the notebook, and I will also advise you to go through a couple of books which I have used to for this particular demo, and all the materials. Okay. So with that being said, if you have any questions, feel free to ask. We can take it along the way, or we can cover it after the event. Okay. All right. So let's get started. So this is something that I have learned, or I've been developing this when I was reading this book, Building Large Language Model from Sebastian. So Sebastian is a very famous author around machine learning. I've been following his book and his DL courses, university course for quite some time. I would strongly recommend you to go over that. And what we are going to do now is we will see that how you can create embeddings from scratch, right? And we will also learn few of the techniques that we use to train any large language model, right? So I will just walk you through as we go along the code, okay? So that we make the best use of this 1 hour. So first, we are going to import torch. So we are using PyTorch for this, but you can always use TensorFlow or anything of that sort. And we are also using our TikTok as a tokenizer. I will come back to this later point in time, right? That is not important at this point. So what we are going to do here is, this is the whole life cycle of building a large language model from scratch, right? I have taken it again from this book. So we start with data preparation, and then we try to build the large language model, and then we train it over training loop. Then we do a model evaluation and so on and so forth. And then we finally do fine tuning. And then the fine-tuned model gets deployed, right? It could be a classification problem or a personal assistant or anything for that matter, right? So anything around text. So we are not talking about images or videos, although we are calling it as a foundational model. So the pipeline is almost the same, but the way that we do the embedding for text and the way that we do the embedding for video and audio is a little different, right? So for the purpose of today's discussion, assume that everything is in text. Okay, so we are building a language model. Now, first, why we need to do that, right? So when we think about large language model, why we even talk about embedding? The reason that we talk about embedding is because the data that we have, this data like video, audio, or text, these are not understandable by the large language model. So they don't understand that. So we have to somehow convert this data into an array of numbers, right? So as simple as that. So all we have to do is we have to convert the data into an array of numbers. Now, how we convert this data to this format is what today's session is about. Okay. And why we are doing this? because these are the numbers, or this is the format which any large language model understand. Okay, so let's take a simple example, right? So in real world, one second. So in real world, the way that you create that embeddings or the array of numbers, that is of very, very high dimension, right? It could be thousands of numbers that you represent a particular word or a particular text. So to give you an example, in let's say we just try to project any word or any token in two-dimensional, like this is the first dimension, the x-axis, and there is a y direction dimension. In that case, you will see that all the words which are similar words will be clubbed together in the same space, so that if you draw a line from this center, like a 0 0, right, from the origin, let's say you draw a line from this origin to eagle and draw a line from the origin to duck, the angle between these two would be very, very small, so the cosine similarity is very high. So that's how we try to encode the context of the words, right? So now how we come up with these vectors, right? So in this case, we have just considered a two dimension, but in real world, it would be hundreds, thousands of dimension, right? So now let's see how we can start by doing this. So this is how a particular any large language model are being trained. Generally, there are some modifications, but if we consider any decoder kind of a model like GPT, we give the text, like let's say this is an example, and then it goes through a tokenization where you split the text into words or subwords. We will see that now. And then we convert it into an ID where each ID belongs to one of the token. And then finally, we get into the embeddings where each ID gets converted into a vector, right? So in this case, previous case, every point is a two-dimensional vector, but in real world, this would be a huge dimension vector, right? Here, for the representation purpose, we have, we can see that there are 3 blocks. That means it's a 3-dimensional embedding, but in real world, it would be 1,000. So now let's talk about how we first convert this data, let's say any text, into these tokens, right? How we can split this. So when you think about token, for now, just consider token as individual words. That's all. Okay. So let's see how we can do this. So for this demo, we have one text file. I have downloaded it from this wiki source. This is a verdict. This is one of the book or the story. I have not read through this, but I'm just using this. Okay, so I've already downloaded it in my local directory. If you see this, this is the text file, right? You can also download that. What I'm doing is I'm simply reading that, and then I'm just checking the length of the whole file, right? So there are 20,000 characters in this. It's a character, right? It's not the word, it's a character. Now, how we can first tokenize it. The simple way to tokenize this is using a split, right? So we can just split based on spaces. So if you see this, we have this space separated text. So we are just doing it for a normal text, like this is just a text string. But later on, we will do this on this entire corpus of data, right? So this is working fine, but a lot of times, and in fact, in this case as well, if you see that we have white space and we have multiple times we have white space, and the only way that this split worked is based on spaces. But what if I don't want space? I also want space, comma, full stop, whatever it is, right? And as a separator. So I can use those as a separator as well. This is just using a regex. And now I see that there are different tokens or there is no, we have not talked about token as of now, but you can see that the text has been divided into different chunks, and each element is divided by either comma, full stop, or spaces, right? But here, if you see, there are multiple spaces, multiple white spaces, right? So if you see that there are multiple white spaces. Now, how we can mitigate that? We can do the same, but then we can just run the strip function, right? So it will just strip out any white space. So this looks good, right? So this is pretty good, and we are able to convert the data into small tokens. Now, if you see this, what has happened is we have converted the data into this tokenized text, right? Now, let's do this for our document, right? Which we have the raw text, which is nothing but this whole wiki source, right? This book. So we are doing the same thing, but now in this single cell, right? And then we are just printing the first 30 tokens. And if you see this, these are the first 30 tokens, right? I had, always. And if you go to this book, we had the same thing, right? I had, always, and all that. Okay. So now, if you see this, the length of this whole document is 4,649. So this is 4,649 words, right? Or words, or any character, like any special character like comma, double hyphen, and all this. So we are kind of done with the first stage where we converted the text into an array of tokens. Now the second task for us is to convert this text into a number. So we have to assign one number to each of these text, right? So how we can do that? So we can simply use a dictionary, and we can iterate over all the tokens and assign a serial number starting from 0, all right? So we can do that, but before this, we have to make sure that we are just considering unique words, right? Because here in this text, in this whole text, we have 4,649 tokens. So what I'm trying to say is, here, if you see, there is a word the, right? So this word the is there somewhere else as well, right? So if you see here, it's I. So I is here as well. So we have to make sure that we need to give unique tokens, right? So for that, what we will do is we will first create a set. So this will eliminate any duplicates, and then we will sort it, right? So that it is in the ascending order or the descending order, whatever you want. And now, if you see, the token size or the vocabulary size is 1,159. So it was 4,000 something, but now it is 1,159. So these are the unique words that I have. Now, to create a mapping between each of these 1,159 tokens to numbers, we can simply iterate over it using enumerate, and we can just say, we can just create this dictionary comprehension where the key is the token and the value is the integer, right? It's pretty simple. And if you want to see the first 50 tokens, it would look like this. So since we have sorted, so that's why it is in this format. But if you do the reverse sort, you will see, bigger words in the beginning. All right. So we have our vocabulary. So this is the vocabulary, right? So this is the whole vocabulary of our for our embeddings that we are going to use, right? So in real world, in large language model, this vocabulary is built using the entire internet scale data. It's the entire internet scale data. So imagine that if you read the whole data which are available in on Wikipedia, I might end up having a vocabulary of more than 100,000 tokens, right? Or even 1 million tokens. That means 1 million unique words or unique characters, right? So for us, the whole vocabulary is nothing but this whole text, right? Just imagine that this is the whole vocabulary of English. Okay, so we are done with this. So now what we can do is we can simply create, put all this code here, and we can create a new class, and we can have two functions, encode and decode. And why we are doing this? Because now you have your entire vocabulary, right? So you can think of it like you have this whole dictionary of your data, right? Where in this dictionary you have the token and its ID, token and its ID. So now, if you give me one string, I should be able to tokenize that, right? Provided the string that you are giving me contains all the tokens within the vocabulary that I have, right? If there is any token that you give which is not present, in this, then it will give us some exception, right? So that is not something that is expected, right? So it's just like if you have, if there is a new English word which gets discovered or invented today, right? You will not find it in the Oxford Dictionary, right? Because it was invented today, and you will not be able to understand what it is, right? So here we are creating this class called simple tokenizer, and we have two attributes. One is string to integer, which is nothing but our vocabulary. And the other one is integer to string, right? Because we might have to convert the tokens into ID and ID into tokens, right? Vice versa. And we will see that, next. So it is just a simple lookup we are creating by just reversing the key to value and value to key, right? And how we are encoding it? We are encoding it in the similar fashion, right? We are doing some pre-processing, and then we are just sending the IDs. Similarly, we are doing decoding. So let me execute this. And now let's try to send one text and see how it gets encoded, right? So now we have the vocabulary, we have the dictionary, right? So this is the vocabulary that I have. Now I should be able to convert any text using this vocabulary. So let's try this. So this is the tokenizer. I'm creating this tokenizer using the vocabulary that I have, which is 1000 some tokens. And then we are just throwing one text, right? So this is just the text, and I want this to encode this. So let's try this. And you see this, we get an array of numbers. And this means that all the words that I have mentioned here, those were part of this vocabulary, right? So this is working fine. And if you want to decode this, if we send this IDs back to the decoder function, we get the actual text again, right? So this is working perfectly fine. So now we want to do something else as well. So now we want to add some special tokens. Okay. So what are those special tokens? These special tokens are the tokens which we will add in case there is an out of vocabulary word come in, right? So because in that case, what will happen is we should get an exception, right? And there is another token which we will add called end of text. And this is important because in large language model, generally what happens is you will put a lot of documents together. So how will I understand that one text, one document is over and the second document is started, right? So that is where the end of text token comes in. So these are the two special tokens we are adding. So in GPT-2, if you see, if you read the paper as well as if you see the code, you will notice that it doesn't have this end of text token, right? So because the way that it has been architected, it is not needed, right? But in general, these are the tokens that you will see, beginning of the sentence, end of the sequence, beginning of the sequence, and padding. So padding is when you have a larger context, but your size is smaller, you have to pad it, right? So for now, you don't have to worry about this. All I wanted to say is we are adding two special tokens, but these tokens are not used in GPT-2, right? Because that is not needed. Okay, so now let's try this. So this is what I was trying to say, right? End of text. When you have multiple documents, so we will add end of text in front of every second text, right? So the first text will not have because that is the starting, but this one will have that. So that when you encode the whole document, right, the entire corpus of data, you know that when the first PDF document is ending, when the second PDF document is starting, and so on. So now let's try this, okay? So before we do this, before we add this new token, let's see what happens when we pass this text. So if you see this, I have just passed this text and it says that key error. Why we are seeing this? Because this word hello is not present in this corpus. So if I do and control F hello, you see that there is a zero output, right? So that means this word is not there at all, right? So that's why we are getting this error. So to mitigate this, we have to add that special token. So what are these special tokens? The special tokens are these two. One is for unknown, one is for end of text. And now, if we see the length of the token, we have increased by 2. It was 1159, so it is now 1161. Okay. All right. So once we have this, we can see the length of the vocabulary. That's absolutely same. And if I now see the last 5 tokens, you will see that we have added these 2 new tokens. Okay, so now let's modify our class. Simple tokenizer. Now we are creating version 2, and it's the same code. So I'm not repeating it. And now if I add 2 text, right? So this is the first text and this is the second text. And now if I just create one text like this, right? So this is the end of the first sentence, right? Or the first document. This is the start of the second document. And now if I encode this, you see this, the array of numbers. And now we are not getting an error. And if you see this, we got and token ID 1159 and 1160, which is an unknown token, right? Because this hello was never in our vocabulary. And now if we decode this, we get the same thing, right? It's unknown because that is the unknown word. And then we got the rest of the text as it is, whatever we had here. Okay. All right. So that is how we were able to create a tokenizer, right? So now what we are going to do is, in real world, if you think about it, this is not very feasible, right? Because every word as a separate token, it's not very feasible because in that case, there will be a n number of words, right? It's an infinite, I mean, not infinite, but the number of tokens that we can have is enormous. So that is not a good practice. And similarly, we can have a small set of vocabulary which may comprises of only, let's say, characters, right? And maybe numbers and special characters. That's all. So in that case, there will be a lot of permutation combination of each and every word, right? And in that case, what will happen is, just imagine if my vocabulary is just A to Z, right? That is 26. In that case, to encode a particular sentence, let's say to encode this particular sentence, right? We would need a huge array, right? Because that would be so what I'm trying to say is, let's say I have this text, right? Let's say I have this text. This is, I'll just copy it from here. Let's say I just copy this first line, right? And if I just have this text, right? And if I just see the length of text, length of T, that is 326. And that means 326 single characters, right, that we have. And let's say each character we later on convert into a vector of size at least, let's say 1556. This is just a random number. So this is the vector that will get generated just to encode one single line, right? So just one single line. So that is not good, right? So there must be some smarter techniques that we should have. So that is where we have BytePair encoding. But before we go there, I think there is one question. I'll try to take that. So typically there is a question. Typically, ChatML also uses some special token signal. Yes, so special token is used in many languages or many models, and in few models they don't use that, and there is a different techniques, right? So in those cases that is not needed at all. For example, for GPT-2, we don't need padding because padding is not needed because when we do when you look at how the model behaves, it just see the data. It just generates one word at a time. And when it generates one word at a time, it doesn't see anything beyond that, right? So, and we will see that in action. So that's why padding is not that needed. So there is one more question. I'm making a resume classification ranking system using NLP. Cosine similarity might not and might go with DNN. How is it feasible? Yes, it's absolutely possible. So we will discuss on that maybe towards the end. Okay. So think of it like this. Okay. Whatever we are doing now, is applicable for any problem, because what we are essentially doing is a pre-work before we even get started with a classification task or any summarization task or anything like that. All we are trying to do is we are trying to convert the text into numbers or an array of numbers so that I can make use of this with any large language model. Okay. All right. So now let's see what is the smarter technique to encode this data. So there is a technique called byte-pair encoding, and that is what is very, very interesting. Okay, so let me just show you one example. So this is from there is one guy called Arun. He's a phenomenal guy from IIT Madras. And this is from Mitesh, Professor Mitesh lecture notes. And I thought that this is the best notes that I've seen. So let me show you how this works. Okay? They have a beautiful animation. So imagine, so the problem that we are trying to solve here now is we want to build our vocabulary in a smarter way, not based on single character, because that is very short, and not based on individual words, because in that case, there will be a millions of words. We want something in the middle, right? How we can go something in the middle is what our objective is, okay? So imagine this is a text, right? So this is, let's say this is the text that we have. And uh, to, to put that in context, uh, we will later think that this one line is nothing but the entire corpus of data that we have. Okay. For illustration purpose, we are just going with one line. Okay. So first thing that we will do in byte-pair encoding is we will add this special character /w after each and every word, just to just to make sure that these all are individual words, right? It's nothing fancy. We are just adding this, right? And then what we will do is our objective is to find the most frequently occurring byte pair. Okay, so what does that mean? So first, what we are going to do is we will just count the occurrence of each word in our corpus. So this is our corpus. Always remember that this is the whole universe for us. So now what we will do is we will see that, okay, knowing is coming how many times in this document? So 3 times. The is coming 1 time. Name is coming 1 time, and so on, right? So that is the frequency count. All right. Now that we have this, what we will do next is we will try to find how many times each character is coming in that in your corpus of data. So in this case, K is coming 9 times. And similarly, there will be different characters, because you remember what we said? We said that we don't want only single characters, because that would be very small vocabulary. We don't want individual words, because that would be a huge library. We want something in the middle. So we will start from single character, and we will keep on merging and come to a stage in the middle, right? Depending on where we want to stop. And then we will say that, okay, this amount of vocabulary is good enough for us. Okay. And how we will come from that single character to that middle portion is what byte pair encoding algorithm is. And that is based on merge sort, basically. So the first thing that we will do is we will try to count each character and its frequency, right? So if you see this, n is coming 13 times. And how this 13 is coming? If you see this, n is coming 2 times in this first word. And this word, the whole knowing word, is coming 3 times in my vocabulary. The total number of n's would be 6, right? Similarly, in this, we have 1. In this, we have 2. So total, there are 13. Okay, so that's how we will just make the frequency count of each character, right? So once you have the entire count of the initial token, so this is my initial token, right? So this is my initial token of individual characters. And now if you see this, my initial vocabulary size is only 22. Right? So this is my initial vocabulary size. In real world, it would be huge, because in that case, my vocabulary won't be 13, right? Because in real world, it would be like whole world data I will start off with. So now what we will do is, now we will try to make pairs. So we will try to see that, okay, how many times K and N are coming together? So it is coming 3 times. how many times N and O is coming together, how many times O and W, and so on. Okay. And once we find this byte pairs, we will pick the maximum one. So in this case, the maximum one is IN. So the next thing what we are going to do is we are going to add IN. So we will see that now. So this is how we do the byte pairing, right? We paired each and every combinations of with our initial vocabulary, right? So once that is done, we found out that IN is the maximum. So what we will do, this was our initial vocabulary, and this is the exercise that we have done. So now I will add IN to my vocabulary, right? So I will simply add IN to my vocabulary. But if you see, I have added IN to my vocabulary. That means I have to reduce the count of I and N, because this IN will cover that. It's just like when you do an intersection of sets, right? So if you see this, initially N was 13 and I was 10 and IN is 7. So I have to subtract 7 for both, right? So my final vocabulary at this point is this, right? So this is my final vocabulary. Similarly, I will continue to do that. So if you noticed, my first merge operation has added one new token. My second merge operation will add one more token. So similarly, if I continue to do, let's say 30,000 merges, my vocabulary size would be 30,000 plus the initial set of tokens. Okay, so if you now go back, anytime in future, I mean, in the days to come, if you see GPT-4, GPT-5, or any model, Claude or Anthropic, Claude or Mistral, if they say that they have a vocabulary size of, let's say, 40,000, that means they must have done roughly around 40,000 merges. Not 40,000 exactly, because they will start with some initial corpus, and then they will be doing that many number of merges, right? If they have implemented it using BytePair encoding. Okay, so this is how the whole process will continue to work, and we will try to merge more and more words. And after 45 merges, we will get 45 new tokens along with the initial tokens. So these were my initial tokens, and these were my new additional tokens, right? And once a token is added to the vocabulary, that can also become part of a merge operation. Okay, so this would be a good exercise if you want to implement it from scratch. You may like to implement it while using it before using any package. So now what happens is, now that we have this vocabulary, now when we give a pass a word and pass it through the tokenizer, it will tokenize into this. So this is why we say that we should not say each word as a token. A token can be a word or a subword. And this is the reason why we say that, right? Because when we started the session, we said that you can think of it as each word as a token, right? And we mentioned that later on we will see that is not the case. So this is the right time to mention this, that each word is not a token, right? So each word may be a token, may not be a token, depending on how my vocabulary looks like, right? So this is how it will work. So if you now imagine, right? So now I have my vocabulary size in the middle, not just the character and not the entire vocabulary of words. It is somewhere in the middle, and how much it is, that is completely dependent on me, how many merge operations that I do. Okay, so now let's go back to my notebook, and I think there is one question. How do we know, Jessica is asking, how do you know where to stop when it comes to, and yeah, that's a good question. So this depends on your capability, like how much, what is the capacity of your training, how much tokens that you can manage, right? So if you have a good compute and everything is you don't have any limitation on that, you can have a large corpus, but it's all about your capacity. Okay, all right. So here we are using a tokenizer called tick token, and we can see the version of that. And here, what we are going to do is we are going to use the GPT-2 tokenizer. So what I'm doing here, when I execute this, right? So when I execute this, what I have exactly done is I have taken the tokenizer which GPT-2 is using or have used, right? So if you see this, the vocabulary size of GPT-2 is almost 50,000. So they must have done 50,000, around 50,000 merges, right? If I consider that their initial corpus size was 257, right? And in fact, we can see some other model as well. So with tick token, we have many different models. So let's pick some other model, right? And check the count of the vocabulary. So if you see this is a bigger model, and that's why the vocabulary size is more, right? So as Jessica mentioned, the more the vocabulary size, you have better capacity. Right? You can understand any text little bit better, right? Because it's quite natural, right? You take a small dictionary of, let's say, 1,000 pages, and you take another dictionary of, let's say, 10,000 pages. The likelihood to get a word whenever you have any query in the bigger dictionary is more, right? So it's exactly like that. Okay, so what is the advantage of this? Here, since there is no one word mapping to tokens, the word gets divided. So when you put a very weird word like this, let's say some unknown place altogether, right? So this is not a proper English word. It is still not throwing any error, right? Because this is how the this tokenizer is built, right? And if you see this, when you decode this, right? So when you take this entire array and when you decode this, you get the same text back, right? So if you see this, we get the same text back, although this is not a proper word, right? And if I have used a tokenizer where each word is a token, the likelihood of getting this word in the entire universe would have been zero or very minimal, right? So that's why when you use PPT tokenizer and throw any unknown word like this, you would be still able to get the word back. Okay. Okay, so there is one more question. Is there an algorithm to go over the corpus and run possible combinations of word and subset to optimize the vocabulary the best and avoid the orphan tokens? Yeah, so that's a good question. So what generally happens is when you build a model for tokenizer, like BPT here in this case, we always go through a huge corpus of data. After that, since we know the count of each merges, right? We actually dropped a lot of tokens which did not occur that frequently in that whole corpus of data, right? So we just dropped that. So this is done at the evaluation time. We do a lot of testing. I mean, big companies when we train, they actually train with different hyperparameters. Basically, it's a kind of, it's not a grid search, but you can think of it like a grid search. Like, what should be the right number that I should go with? Like, this is the minimum amount of vocabulary that I should have to get an accuracy of, let's say, some percent, right? It's just like this, right? If I give you 10 different dictionaries, right? So this dictionary contains, let's say, 1,000 words. There is another dictionary contains 10,000 words, and there is another dictionary which contains 1 million words. Now you have a very simple problem of, let's say, I mean, you want to have a dictionary for your kid who is studying in, let's say, fifth grade. So all of these three dictionary will work for you, but you will take the least one, right? Maybe with 100 words, because you are very sure that it should survive for that purpose. But let's say you are doing PhD in linguistics. So in that case, you might need a bigger dictionary. So it depends on the use case and depends on your capacity. You can play around with this and set the right number. All right. So now that we are done with tokenization, now comes the second important thing is that how we will send the data for training, right? So this is where things are get little interesting, right? At least when I first learned this, I just loved it. So now that we know, so let's recap, right? What we have learned so far. So we learned that LLMs cannot take plain text. So we have to convert it into numbers. So, or array of numbers. So we have taken the first step to take any text and convert it into small tokens. So we are done with that. As of now, we are done with that. Second stage is also done, where we took that token and converted into IDs, token IDs, right? So that is also done. So which we have done it here itself, right? So we pass the word and we get the tokens, right? We are good with this. So now, how we can use this text and how we can train a large language model, right? Because ultimately, this is what we have to do, right? So the way that we will do this is like this. So in GPT-2 or any language model, what they do is any decoder-based transformer, what they do is you give any string, it just predicts the next word. So you give this, let's say this is one sentence, LLM learn to predict one word at a time. The first sample would be LLM, and the expectation would be it should predict learn. Similarly, the next sample would be LLM learn, and the prediction should be, or the class label should be TO2. Okay. So now let's see how we can generate this data set using sliding window. So again, our text file, right? We are just reading it. It's still, I still have it loaded in this variable, but just for completion, I'm loading it. And if we see this, we have encoded it now using our GPT-2 tokenizer. And this means that it has 5,000 tokens. Okay, so this our entire corpus of data contains 5,000 tokens. Now, if I'm just removing the first 50 tokens because it has some garbage data, so that is not needed, right? You can always do this. This is just for cleaning purpose. There is not a step that we should do. Okay. So now, what we have to do first is we have to first define what should be our context size. Okay. So in this case, the context size is 1, 2, 3, 4, 5, 6, 7, 8. Right? Because at max you can have 8 words. So in this case, what we are going to do is we will, let's say we will pick a context size of 4. So that means that whenever you want to predict, maximum you can have the context size as 4. So let me show you how this would look like, and then you will get an idea. So what I'm doing here is I'm taking this sample, right? This is I'm just taking the this sample variable, which contains the list of tokens. I'm just taking the first 4 tokens, right? So this is the first 4 tokens, and this is the X, and this is my Y, right? So if you think about it, it would be like this. When the input is this, the expectation is this. When the input is this, the expectation is this. When the input is this, the expectation is this. When the input is this, the expectation is this. So the reason that I repeated this is because just to give you an intuition that what we are essentially doing, we are sliding over, right? We are just sliding over. And if you see this in a pictorial fashion, this is what my input and the class variable would be. Right? This is the input, this is the class variable. This is the input, this is the class variable. And if I decode it, it would be like this. When the word is token is and, the expectation should be established. And when the token is and established, the expectation would be himself, like that. So this is how you can use your data using sliding window to train any large language model. Okay. So if you think about it, we could have, you can say, hey, Suman, why I'm doing all this, right? Why we have to slide? We can always create individual X, Y, right? So the first X would be this, and the first Y would be this. This would be X2, this would be Y2. But if you think about it, the challenge with this is you have multiple entries unnecessarily. And second, the size of the input is different, right? But in this case, what we have done intelligently, we have kept the size constant and we say that, okay, just slide on, right? It's just a for loop, right? So this is how you will tokenize. And to put that in context, how the tensor would look like now. Now, again, we are considering a context window of 4. In real world, it would be much more, right? So you can scale it, right? So that's the beauty of mathematics and linear algebra, right? So you don't have to worry about the dimension. So if you see this, when the input is in the heart of, the expectation would be the, right? And if you read the sentence, in the heart of the city, right? So you get the idea, right? How you will slide and how your X tensor would look like and how your Y tensor would look like, right? So now what we are going to do is we are going to create a data loader, right? So all concepts that whatever we have learned is implemented in this for loop, right? Nothing fancy. And once we have our data loader and we are putting all the code, whatever we have learned, so we are creating a GPT-2 tokenizer. We are using the data set, what we have coded here, where we have implemented this sliding window, and that's all, right? So now we have our data loader. And now we will do the same thing. We will read the text file. I'm doing this again and again, although this is the same thing. Just to, when you run this in your laptop or in your machine, you get the context, right? I don't like to use a variable which I, which I use, let's say 100 cells above, right? So it doesn't give any context. So I'm just reading the whole file. And now I am creating a data loader. And if you see this, my first data loader, first fetched pair of X and Y is this. The next of X and Y is this. So imagine if the context window was not 4 and the data set was huge, right? Then it would have been the same thing, right? Depending on the how many context window that you want. I mean, how much context window you want. So in this case, the max length is 4, and I'm striding with one token at a time, right? So I hope you get this idea. This is the same thing in a pictorial format. So this is taken from the same book. And that's all, right? So if you see now, our entire corpus would look something like this. And this we can use for our training. But we are not yet over, right? Because what we have done is we have converted the text into token ID. But now we have to convert each of this token into an array of numbers. If I just scroll up, if you remember here, we are done with this. We splitted the tokens, right? Then we have converted into numbers. Now we are in this position, right? We have to create each token into an array of numbers, right? So just like in this example, we used each token in an array of 2 numbers, right? First dimension, second dimension. Now we have to do the same thing for our vocabulary, right? So let's try to do that. Where are we? Okay, yeah. How we can do the embedding? Oh, the image was here only. Okay, so how we are going to do this? So for the sake of example, again, we will do the same thing on our corpus of data, but let's take a small set of IDs. So this is my, let's say this is my input IDs. Okay, so this is my input IDs. And imagine that my vocabulary is only 6. Okay, only 6. That means only 6 elements, tokens that I have in my vocabulary. And the embedding size is 3. That means every token should be embedded with an array of 3 numbers. So the way that I can create an embedding layer using torch.nn.embedding, we can give the vocabulary size and the output dimension. And if I see this output, right? If I see this output, I see an embedding matrix. So what this matrix means? This matrix means if the token ID is 0, this is a vector. If the token ID is 1, this is a vector. If the token ID is 2, this is a vector, right? In real world, these numbers are also trained. These are also trainable parameters. In real world, when you do the training in mostly any model, GPT-2 or any state-of-the-art models, these embeddings are also trained during the training process, so that the right how can I say, the right embedding comes for each and every token. Okay, so now if I just use this embedding layer, and if I say that, okay, what is the embedding of token 3? You will see that this is the output. And if you see this output is exactly same as the fourth row of this because the indexing starts from 0. So this is the fourth row. All right. So this is how we can convert our data into an array of numbers, right? So in this case, we have taken an example of 3, right? But in real world, it would be it would be quite large, right? But in this case, there is one problem. You might have noticed this. If I have a text like this, right? Just focus on this. The text is fox jumps over the dog. So the fox has an embedding ID of 2, right? So this is the embedding metric. So the second element is this row, right, which is in blue. Now let's say if I have another word like this, another sentence like this, where I have the same word but in a different position, right? My embedding would be still the same. So what I'm trying to say, I think it is not mentioned in this slide. I'm sorry. Yeah, I'm sorry. It is in this. So if you see this, the fox here is used in the first word, and here the fox is in the fourth word, right? But still, the embedding is same. So that means I'm not able to retain the position of the word in the sentence, right? When I encode this, I'm losing the location of the word. And location of the word makes a huge difference in real world, right? So where you say a particular word in a sentence, that depends on the context, right? Where that word is placed. So somehow we have to inject the positional information in our embedding. So imagine this is our tokens. This is our token embeddings. In this case, if you see this, these are all same token. So imagine that 111 is the same word we are repeating 4 times, right? Let's say a sentence is the, right? So what we have to do is we have to add some positional embeddings, which will which we will what we will do is which we will add with the embeddings and then make it as an input embedding. Okay, so what I'm trying to say is that somehow we have to add positional information to the embedding that we have already created. Okay, so now there are different types of techniques to add positional embeddings. We are going to use absolute positional embeddings. Okay, so what that means is every position has a unique embeddings. Okay, every position 1 will have a unique embedding, position 2 will have a unique embeddings, and so on and so forth. Okay, so in this case, let's say my vocabulary size is this, the output dimension is this. Okay, so now we are going little real world. So my vocabulary size is 50,000 and my output embedding is this, right? So what we can do is we will create a embedding layer. This simple. This is something that we have done before. We are just using the data loader. So this is the token IDs, and this is the embedding layers. And now, if you see here, what we are doing is we are creating a positional embedding, right? Again, using embedding, but in this case, we are just going to add this. Simply, we are going to add this embeddings with the already created embeddings. Nothing fancy, okay? So if you see this, the input embeddings would be the token embeddings plus the positional encodings. That's all, right? And if you see this, the positional embedding shape is 4 cross 256 because every vector is of 556 dimension, right? And then once we add that, we get a new dimension, right? So in this case, if you see this, so how we started off with this sentence, then we split it into words, then words into token IDs, then token ID to token embeddings. Till this part, it was fine. But till this part, we are not able to retain the information of the position of the word, right? If the word the is present here as well, the embedding for this the and this the would be same, but that is not true, right? So we should add that information. So that's why we are adding a positional embedding. So we are adding another layer where this will be completely static, right? The first word should have a static embedding, second word should have a static embedding. We will just add that so that in real world, when you get this embeddings, right, I can come back to this actual words. I will just subtract the positional embedding because I can always do that subtraction. And if you're curious how it in real world, how this positional embeddings are generated, that actually uses something called Fourier transform. I'll just quickly show you because I'm almost done with the session, but this is something I find it little interesting. So how this positional embedding works is something like that. So imagine that here, just focus on what I'm saying, okay? Imagine that I just need 4-dimensional vectors. That means my embedding layer will convert each token into 4 numbers. So my positional embedding should also have 4 numbers because only then I can add. So this is the graph. And the way that I generated this is using random sine waves and cos waves. Okay, so there is some sine function, there is some cos function, and how many of such function I should take, that depends on the dimension. So in this case, I have taken a dimension of 4. And the x-axis is nothing but the position of a word in the sentence. So in this case, if I pick this, which is kind of the 30th position, the embedding, positional embedding of this 30th word would be the value of all these 4 waves or all these 4 signals. So this would be like something around 0.9, then 0.25, 0.25, and minus 0.99, right? So, I have already written here. So this is the positional embedding for any tokenizer where the dimension is 4. Okay? It's a continuous function, so you can have the length of the sentence can be 100, 1,000, 2,000, whatever. But what I'm trying to say is how we generate these positional embeddings, right? So you can think of it like that. If somebody tells you that, okay, I want to build a tokenizer which can, which has a token length of 1,000, the the dimension of 1,000. That means every token you will convert into an array of 1,000 numbers. What you will do is you will just generate 1,000 sine waves and cos waves. So maybe you will have 500 sine functions, different sine functions, and 500 cos functions. That's all. And then you will just put it in a chart, and you can just take every function's combination of all these functions value at different positions. That's all, right? It's nothing very fancy. So there is a scientific paper as well if you want to know, because positional embedding is very, very important. You can read the paper of Bert, and there is one slide. I have this quite some time back, but I'll share this link as well with you. Maybe somebody from the team can share. And if you want to know more about this, you can ping me. I would be more than happy to share this with you. And with that, I will just share a couple of things. So this is the GitHub repo which contains that notebook, right? So which I have. I will share it, and somebody from the team will put that. And this is the slide deck. I would strongly recommend that you can go over this. All thanks to IIT Madras professors. And also, there is a GitHub page that I have, which contains more on Bedrock side, like how you can do all this, use it with RAG and other things. This is a good repo. There are a lot of demos, and I keep on adding things here. So you can go over this. And also, there is one blog post which I have written some time back. So let me show you this. Yeah, this one. This is a place where whatever you have learned, it's kind of the core of this. But let's say you want to take this learning to the next stage and how you can make use of this with RAG, where we do semantic search and all that. You may like to refer to this blog, right? So it contains how embedding works and with little more details, and then how you can make use of that with Bedrock. Okay, so with that, I'm done with this. And if you have any questions, I can take, and yeah. All right, let me just go over this.